So we're going to talk about the pH scale. On the left here, this arrow shows the pH scale. pH is typically considered somewhere between 0 or 1 and 14. However, you can have pHs that are negative numbers, and you can also have pHs that are greater than 14, but they're not going to vary much beyond this scale. And you can see there's a relationship between hydrogen ion concentration and pH, and we're going to talk more about that. But let's call our attention to water in the middle, which has a pH of 7 and is considered neutral, neither acidic nor basic. This equation describes what's called the autoionization of water, where a water molecule will dissociate into a hydrogen ion and a hydroxide ion. So that's what this equation describes, is the autoionization of water. Auto meaning self, right, and ionization meaning it forms ions. And so this will happen because the bond between the oxygen and the hydrogen will break, and the oxygen will take those electrons away, leaving hydrogen with no electrons. That would be H+, and then having hydroxide as with a -1 charge. This has an equilibrium constant called Kw. The W stands for water, and Kw at 25 degrees is 1 × 10⁻14. This lies far to the left, as you might expect. Water is a very stable molecule. It doesn't tend to autoionize to a very large extent. So most of this is left as water, and a very small amount forms hydrogen ion and hydroxide ion. So this is the next thing I want to talk about, is what the concentrations of these ions are. So here is our autoionization of water equation. We have Kw. We know it lies far to the left because it's a really small equilibrium constant. And we're going to figure out the hydrogen ion concentration and the hydroxide ion concentration so we can talk about the pH of pure water. So remember, when we do this, we need an ice table because this is an equilibrium expression. We can write the expression for Kw. And it doesn't really matter what water is because it doesn't appear in our equilibrium expression. So let's remember that pure solids and pure liquids don't appear. So our equilibrium expression for Kw is H+ concentration times OH minus concentration. Remember, the brackets mean concentration. And so if we know the equilibrium constant is Kw, 1 × 10⁻14, then we start with 0 hydrogen ion and hydroxide ion, and then we add X to both sides because water is going to dissociate to some degree. And we get X at equilibrium. We plug that into our equilibrium expression. So X squared. So 1 × 10⁻14 equals X squared. And then we simply have to solve for X by taking the square root of both sides, which means that X is equal to 1 × 10⁻7, which means that in a sample of pure water at 25 degrees, the concentration of hydrogen ion will equal the concentration of hydroxide ion because they dissociate. Whenever you form 1 mole of one, you form 1 mole of the other. The stoichiometry is 1 to 1. And therefore, they are both 1 × 10⁻7 in pure water, molar, of course, and this is at 25 degrees Celsius. Now, if we come back to our pH scale, and we look at the relationship between hydrogen ion concentration and pH, what you should notice is that the pH is related to the hydrogen ion concentration by that exponent, right? So when the hydrogen ion concentration is, if we look at the very top one, 10⁻14, now remember that's a really small number, right? So 0.00000000000001, that was 13 zeros and a 1 is 1 × 10⁻14. That gives a pH of 14. And so whatever this exponent is up here, the negative exponent is equal to the pH value, right? So let's see if we can think of a mathematical way. It's a negative logarithm relationship, logarithm base 10. So pH equals the negative log of the hydrogen ion concentration. Now I put up here hydronium ion concentration. Remember that those are the same thing, okay? Now if we come back to our expression here, if we know that this is Kw, this relationship will hold in any aqueous solution at 25 degrees. So what that means is that once you know the hydrogen ion concentration, let's say it's not pure water, let's say it's hydrochloric acid, and you have some amount of hydrogen ion concentration, say it's 1 times 10 to the minus 2 molar, then that means that your hydroxide ion concentration must be 1 times 10 to the minus 12 molar, because they have to, their products have to be 1 times 10 to the minus 14. When you multiply the hydrogen ion concentration times the hydroxide ion concentration, it will always equal Kw. So if you know one of them, you automatically know the other one. Now it says here at 25 degrees, remember that equilibrium constants, including Kw, will vary with the temperature. So at higher or lower temperature, you'll have a different value for K. Now if we come back to this idea of acidic, basic, and neutral, in the middle here we have a neutral solution where the hydrogen ion or hydronium ion concentration equals the hydroxide ion concentration. They're both equal to 1 times 10 to the minus 7 molar, which would give a pH of 7. Now if we look instead at an acidic solution, that would have a larger amount of hydronium ion and a smaller amount of hydroxide ion. You're still going to get 1 times 10 to the minus 14 when you multiply them together. And that would have a pH of less than 7, right? And then on the right-hand side, we have a basic solution where the hydroxide ion concentration exceeds the hydronium ion concentration. They will still, when you multiply them together, give you 1 times 10 to the minus 14, as long as you're at 25 degrees. Now we're going to complete this table because now we know how to do hydrogen ion. We know that we can interconvert these values. Okay, so in this table you have 4 different solutions. And so for the first row, if you know the hydrogen ion concentration, we're going to calculate the hydroxide ion concentration and the pH and a value called the pOH. So we're going to practice converting hydrogen ion concentration into pH, or vice versa, hydrogen ion concentration into hydroxide ion concentration. And just as an intro to that, keep in mind this is something we talked about in class, but if you know the hydrogen ion concentration, you can convert it to pH using the equation pH equals negative log of H plus, or you can convert it back using the hydrogen ion concentration equals 10 to the negative pH. So once you know one of these, you can calculate the other one. You also can convert hydrogen ion concentration into hydroxide ion concentration, or vice versa, using the equation Kw equals H plus times OH minus. Kw is on the yellow sheet, but it is equal to 1 times 10 to the minus 14 at 25 degrees Celsius. You can also calculate pOH, which is the fourth and final value that we're going to talk about, using the equation pOH equals negative log of the hydrogen ion of the hydroxide ion concentration, or you can convert the other way, the same as above with hydrogen ion concentration, that the hydroxide ion concentration equals 10 to the negative pOH. Finally, the last equation that you can use is that pH plus pOH, the sum of those two numbers should equal 14 for a given solution. So in summary, once you know one of these values, any of the 4, you can calculate the other 3 using this set of equations. By the time you get to the 4th one, if you're actually calculating all 4, by the time you get to the last one, there are going to be 2 ways to solve the answer. We'll talk about that when we do these practice problems. We did some of these in class together. We're going to do them all again. Some of these we didn't do together, but we did the first row and the third row. But we're going to repeat it here in case you need to see it again. But you can always fast forward if you don't want to see it. So this first box, hydroxide ion concentration, we can calculate from hydrogen ion concentration using the equation Kw equals the product of those two. So you just plug the numbers in, and you get that the hydroxide ion concentration is 8.3 times 10 to the minus 12. I'm going to put that in the box. The second box, pH, we're going to calculate from hydrogen ion concentration. It's the negative log of 1.2 times 10 to the minus 3, which is 2.92. Sig fig wise, we're going to write 2.92 in the box. Remember that the significant figures for logarithm, you keep the same number of digits after the decimal as the total number in the number that you're given. So 1.2 times 10 to the minus 3 has 2 sig figs, which means 2.92 has 2 digits after the decimal. pOH is the negative log of the hydroxide ion concentration, or 14 minus the pH, which gives you 14 minus 2.92, which is 11.08. Another way to do this problem is that pOH is the negative log of the hydroxide ion concentration, which is here, 8.3 times 10 to the minus 12. Solving it that way should give you the same exact answer. And the same sig figs. So row 2, we're going to start by calculating hydrogen ion concentration from hydroxide using the Kw as the product of those two. Plug the numbers in, you get 2.3 times 10 to the minus 10 molar. pH is the negative log of that number. I put in the unrounded number here because it might slightly change my answer to have the rounded number. So whenever you're doing a calculation, you should use the unrounded number in your calculation. Let me know if that doesn't make sense, but 2.3 might change my answer slightly, so I'm not going to change it. So 9.63. And then pOH, we can solve one of two ways. It's either the negative log of the hydroxide ion concentration, 4.37, or it is 14 minus 9.63. There's always sort of two ways to do the last one. That should still give you 4.37. It shouldn't matter. But you can always use that as a check. Yep, got the same answer. That's good. I feel good. Now we're going to erase that and do row 3. We start with 5.42. We did this one in class, actually. We're going to start with the hydrogen ion concentration, which should be 10 to the negative 5.42, which is 3.8 times 10 to the minus 6. Then we can calculate the hydroxide ion concentration from that number, knowing that the product of those two numbers is Kw. Plug in the numbers. Use again the unrounded number here. I rounded it here, 3.8, but the actual number was 3.80189. And then you plug those in and you get that the hydroxide ion concentration is 2.6 times 10 to the minus 9. Again, I don't want to get rounding errors in my answer. That's why I use the unrounded number. pOH is 14 minus the pH, which is 8.58. Or we could have used the hydroxide ion concentration and solved it that way. That should give us the same number, 8.58. It would have been 10 to the negative 2.6 times 10 to the minus 9 should also give you 8.58. I'm sorry, the negative log of 2.6 times 10 to the minus 9 should still give you 8.58. Now this box here, hydrogen ion concentration, we can't actually calculate that directly from pOH. This is the only calculation you can't do directly from pOH to hydrogen ion. So we're going to start by calculating pH from pOH. I'm going to do this box instead. So that's going to be 14 minus 4.39. That's going to give me 9.61. I'm going to put that in the box. Now I can calculate hydrogen ion concentration because that's going to be 10 to the negative 9.61, sorry, and that's going to give me 2.4 times 10 to the minus 10, or 2.5 times 10 to the minus 10. The reason is because the answer is 2.45, and it depends on how you round 5. If you round it up or you round to the even number, either way, that's acceptable. The last calculation here is hydroxide ion concentration. Can either do 10 to the negative pOH, 10 to the negative 4.39, which gives me 4.1 times 10 to the minus 5, or I could have calculated it from the hydrogen ion concentration. It would be Kw divided by this 2.4547 times 10 to the minus 10 number should still give you the same value here, 4.1 times 10 to the minus 5 molar.